Okay. All right. Long time no see. All right. Are you excited for Thanksgiving?
Very excited, extremely.
Yes. Do you have a lot of homework?
Yes.
Hmm.
Fermentation blend.
Oh, I didn't say when your lab report is due.
Yeah.
Did I?
No.
Monday. No. 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 Actually, we're giving you 2 extra days, so it will be next Friday. So, yeah, of course. Charu, you're going to send them the data without your wonderful entries. Okay. So this goes to both groups today, please. Okay, both lab groups. All right, so let's just refresh your memory. We started talking a little bit about pH and the difference between pH and total acidity. If two acids have the same concentration, do they always have the same pH? Shamili?
No.
No, why not?
Some things like the ionization strength and also like the hydrogen bonds.
Yes, so it depends on the dissociation of the acid. So you might have acetic acid and you might have HCl. HCl is highly dissociative, dissociates almost completely, whereas the acetic acid is the organic acid, it doesn't dissociate completely. So the free hydrogens in solution will be less in an organic acid setting versus a strong acid. So they might have the same concentration, but they will not have the same pH. Not necessarily. How does titratable acidity affect food? What does it affect mostly? The total acid. What does it affect? Alicia. Sourness, sensory perception, yes. Whereas pH, what does it impact? The pH of the system. Microbial activity, enzyme activity, chemical reactions. Thank you. So the pH is important for any type of activity, whether it's enzyme, chemical, or microbial. What is pKa? You remember the very first part of the semester, we talked about preparation of buffers and we talked about pKa. Does anybody remember what pKa is? Yeah, but what is it in common terms? Yeah.
It's when the weak acid and the conjugate base is equal
present.
concentration.
So it's, yes, exactly. It's the pH at which you have conjugate acid and conjugate base, or associated acid and conjugate base are at equal concentration. So this is a maximum buffering capacity. So pKa equal the pH, because if you remember, you don't remember, I'm going to remind you of it. They had this in Hasselbalch equation. pH equal pKa plus log of, see Rachel, the color here? Wonderful. A minus conjugate base concentration over the associated acid. So when the concentration are equal of the conjugate base and the acid, log of 1 is 0, right? Log of 1 equals 0. Then the pH equal to pKa, and this is maximum buffering capacity, meaning you have enough same concentration of conjugate base that can absorb protons and acid that can give protons, so resisting change in pH. Okay. Can an organic acid buffer at multiple pHs? think we mentioned it briefly last time. Why do you think, Mitch?
Oh, because of the chemical carboxyl, it has like six.
How many carboxyl groups? So acetic acid has one carboxyl group, for instance, so it has one pKa, so it buffers at one pH, whereas citric acid has three carboxyl groups. So it can buffer at three different pHs, because each of these carboxyl group will have different dissociation factor. And if they have a different dissociation factor, that means they have different pKas. All right. And here's a lot of what we talked about already. So here it's showing two different acids. This is acetic acid and hydrochloride acid, HCl and acetic acid. What HCl is very strong acid. Citric or acetic acid, sorry, is organic acid, not very strong. Same concentration, different pHs. Why? Because strong acid fully dissociates, weak acid only partially dissociates. So 1.1 normal HCl has a pH of 1. Acetic acid 0.1 normal has a pH of almost 3. So very different pH, same concentration. All right. I want you to pull up a piece of paper for extra credit. We're going to do some solving of equations. But before we get started, as a reminder, we all know from our basic chemistry that acid is a proton donor. So in aqueous, acid forms hydronium ions. H3O plus is hydronium ion. Base is a proton acceptor, forms hydroxide ions. So neutralization, when you have acid and base at neutralization point, you get salt and H2O. The product of the concentration of acid and concentration of base is ion product constant for water. It's always close to 1 times 10 to the negative 14 at about room temperature. So does this minus 14 ring a bell to you? What does it remind you of? The range of pH, the range of pH. Okay, so the product of, so as the concentration of hydronium ion and OH minus or hydroxyl groups differ, while this will add up to 1 all the time, you will have different pH. So here's what I mean. So when pH is 7, you have equal concentration of hydronium ion and hydroxyl group. So, and this would be 1 times 10 to the minus 7 each. So the product is 1 times 10 to the negative 14. pH is the inverse log of hydronium ion, pH. There's POH too, but it's not commonly used. POH is the inverse log of the OH minus, but we don't use it. We use pH, which is the negative log of the hydronium ion. So let's do some calculation to apply this pH. So 7-Up has a concentration of hydronium ion of 3.55 times 10 to the minus 4. What's the concentration of OH and what's the pH? Apply that the multiplication of the two concentrations always 1 times 10 to the negative 14. So apply that to get the concentration of hydroxyl groups and then calculate pH. Take a moment. Anybody close to the concentration of hydroxyl groups? And to solve it. So you have the hydronium ion. What do you get? Yes, Tyler?
Hydroxide concentration of 2.8 times 10 to the negative 11.
Yes, 2.82 times 10 to the negative 11. Yes, applies your mathematics. And now you need to calculate the pH, which is equal minus log the concentration of hydronium ion. So, did you get to that? What is it? 3.45. That is correct. So you just need to apply the calculation using your calculators. If I ask any of these questions in the exam, you will be able to use your calculator. So you just apply that. You fill in. You can do it in any way you want, directly on the calculator. I did it here stepwise. This is how my brain functions, but you can do it directly on your scientific calculator. You can take a picture of that. Okay. All right, so now let's continue with an exercise. You have a beer that has a pH of 4.3. Calculate the concentration. Same, you need to apply this equation. Now you have the inverse, you have the pH. What is the concentration? Again, you can use directly your calculator. You don't have to do it stepwise. I do it usually stepwise. Who has an answer? Razi, you have an answer?
No.
Why? You don't have a calculator?
No, not with me.
Okay. All right. Who has an answer? Okay, I'll give you a moment.
Correct. I got 5.01 times 10 to the negative 5.
Correct. Yeah, like I said, I do it stepwise, but your calculator you can just plug in the numbers and get the log and anti-log. Okay. All right. We good to move on? All right. Very quickly, you will be you already used the pH meter, right? In one of the labs, and you did calibrate it too. Didn't you do 2-point calibration or no? You didn't? You measured the buff when you prepared buffer, did you not measure the pH?
The standard, well, some did,
Okay.
they didn't make every group do it.
Oh, I see. Okay. Now I don't recall in the manual if you have to use the pH meter. You are going to use the pH meter for sure. So probably there is a section for calibration. But just quickly, I'm not going to expect you to know how a pH meter functions, but really very kind of high level. We measure the active hydrogen when we protons. So when you are measuring the pH, we are measuring the active, the concentration of active protons. And the way it works, you actually measure voltage or change in electrical potential when you apply very, very small current, infinitesimal current. So that change in electrical potential is proportional to the concentration of your hydronium ions. This is all what I want you just to high level know about how the pH meter works. There's a lot of information in your textbook about it, but no, I don't expect you to remember that. I'm not sure how the different types of pH meters that you'll see in the lab, but oftentimes you have the probe has both your sensor and your reference. There's always a reference electrode and the indicator electrode. So the reference electrode is measuring that constant current, and then your indicator electrode is picking up the change in that current when a potential is applied, when a voltage is applied. Okay. So, but most modern pH meter, you'll have only that one probe that has the reference and the indicator electrodes in it. So we have to keep, there are certain guidance for use. We have to follow manufacturer instructions. It's very important. So when you are on your own researcher in the lab, you really need to know how to calibrate a pH meter. And usually we use 2-point calibration. So 3, 7, and 10, pH 3, 7, and 10 are very commonly used. You pick 2 of those and do 2-point calibration. Also, your electrode needs to be cleaned. So sometimes if you're measuring protein solution, protein will stick to the probe. If you're measuring fat, something that has high lipid content, the lipid will stick to your probe. So you really want to clean it. And you usually use a combination of solutions to clean it, like alcohol to get that fatty layer out, a little bit of protease, an enzyme to break proteins and clean it. So HCl acid can also be used to clean it. What do we clean our pH mix? With HCl. Okay. Yeah, so every pH meter actually comes with a little bit of guidelines, and then you make sure you follow these guidelines to get rid of the gunk that can be built up when you're using it in different samples. And we have to always store it in KCl solution. We don't want it to dry out. So, and we don't want obviously salt to build up in the electrode either. So proper usage is always important. Okay, so I'm going to move on, talk about how do we measure titratable acidity. You did the fat characterization lab and you did free fatty acids. So it's just titration with base, really, to determine total acidity. So oftentimes we measure concentration of organic acids in food. So in milk, you might be wanting to measure total lactic acid. In orange juice, you measure total amount of citric acid. In the lab, you're going to measure malic acid, which is the main acid in apples. And also you are going to do something else. What are we doing in the lab? 7-Up, was it? Carbonated beverage. Carbonated beverage has carbonic acid in it, which is inorganic acid. Sometimes we have in our beverages that you find in the market, high protein beverages have phosphoric acid. Carbonic acid is present in soda, beverages. And carbonic acid is basically when you bubble in CO2 to make your soda fizzy, CO2 reacts with water to give you carbonic acid. So when we titrate the acid with a base, you can either use a phenolphthalein indicator to determine the endpoint like you did for the free fatty acid, or we can measure the pH change upon neutralization. So bring you back to the principle of buffer. This is important because all of organic acids in food are buffers. And those that are synthetic inorganic acid, phosphoric acid and carbonic acid, they also buffer. So it's really important to understand how do we reach equilibrium. So this is just to remind you that the buffer, it resists change in pH, and it occurs when you have weak acid and its conjugate base. All food acids are weak acids. So buffering occurs in food, and we need to keep that in mind when we are determining total acidity. We want to make sure that we are not at the buffering zone of these acids. And then the Henderson-Hasselbalch equation is important because when we're titrating, what are we doing? So you have acid, you titrate until you get neutralization of that acid. So that is the point. But when we get neutralization, and if you continue titrating, the next drop is going to raise the pH significantly because now you have more NOH and you see a change in color to pink. The last drop after neutralization, the phenolphthalein indicator is going to change to pink, and if you're measuring pH, you're going to see a sudden increase in the pH beyond the neutralization point. So when you are titrating organic acids, so you have this buffering capacity, but all of our organic acids, the good thing about them, they don't buffer around the neutralization pH. So you will get the endpoint, and that's that. There's no buffering happening there. So at the end of the reaction, the way we calculate is we have to remember number of acid equivalents equal number of base equivalent. Now, this is important in titratable acidity of organic acid. Why? Because some acid have more than one H in it, in the reaction. It's not like HCl, you have one H. So you have multiple H's depending on how many carboxyl groups you have. So in your equivalence equation, you have to account for the number of hydrogens that are in the reaction. Okay, so we talked about the rapid increase in pH. And here's a demonstration of a titration curve. You're going to be plotting a titration curve for, I think, citric acid, maybe, and phenolic acid in the lab. Should have looked at the beverages again. So if you look at HCl, so the titration curve for HCl, so you're titrating with NOH. So there is no buffering zone. So the pH increases as you titrate with NaOH, and then you reach the equilibrium point in the midpoint around 7, and then the pH increases dramatically with the next drop of NaOH. So sharp increase in pH. Now, if you look at this is citric acid. So you have 3 carboxyl groups. 1, 2, 3. So how many hydrogens? You have 1, 2, 3 hydrogens that participate in the reaction. So you have 3 pKa's, dissociation constants. 1, 2, 3. So each pKa is different because you have different dissociation constants. So you will see buffering zones, 1, 2, 3 buffering zones. So that means you're adding NaOH and you hardly see a change in the pH. And you continue adding beyond the pKa value to the next pKa, you see a little bit of plateau, to the third pKa, and then you see a sharp increase after neutralization happens. This is acetic acid, so 1 carboxyl group, so we see 1 pKa, 1 buffering zone. So their pH is increasing with more NaOH, we get to a buffering zone, and it increases. We get to the equivalent points, and we continue. After another drop, we see a sharp increase in pH. So this is just demonstrating that the carboxyl groups, number of carboxyl groups in your organic acid is very important in understanding the buffering zones and also are needed for the calculation. Here there's 1 hydrogen, here there's 3 hydrogens participating in the reaction. So, with that said, please apply the Henderson-Hasselbalch equation to determine the percent of lactic acid dissociated. So that means the conjugate base of it. Using the Henderson-Hasselbalch equation. We did some, you might have to remember some of the practice we did before when we covered buffers. You simply apply your Henderson-Hasselbalch equation to calculate the concentration percentage of basically the A minus, your conjugate base. You tell me when you have a value. And then 1 part equal concentration. So the 1 part or 100%, however you want to calculate it, equal the concentration. So in 1 solution, that's why it's 1 part, 1 solution, or 100% is the summation of this conjugate base and conjugate acid concentration. You're all trying, that's good. Anybody, Sierra, did you reach? Okay, that's fine. Are we stuck on anything? Yeah? Where did you get stuck on? Okay, what's the first thing you need to do? Tell me. One of you can tell me. The very first thing you need to do? Just say a word. Nobody's looking me in the eye. Okay. Yeah, arrange the Henderson-Hasselbalch equation. So what's the given, Alicia? What's the pH? 4.7, right? And then we subtract the pKa, you said? Yeah, okay. Let's subtract the pKa. All right, what is the pKa? 3.86. All right. Then this will be equal log. If I'm calculating A minus, the concentration. So I can just put this bottom one with rearranging that equation. So I'm solving for A minus. That would be the log of A minus here over 1 minus A minus. So if you do the math and the log, what would be the ratio of A minus over 1 minus 1? What's the ratio for that? What does your calculator tell you?
I got 6.9.
6.91. Let me see. 6.92 I got. 6.92. Very good. Then now I solve for A minus. So I have here, if I do just the algebra part of it, 6.92 minus 6.92A. Then now I have 1A here, then it will be, if I bring this over, then it will be 7.692A minus equal 6.92.
0.9,
Huh? A minus equal
7.9. Yeah. Yeah, 7.92.
7.92. What did I write? Oh. Ah. Thank you. All right. So then my A minus equal 6.92 divided by 7.92. What is that? Point 8 9
7.
7. Very good. So if I'm looking at a percentage, that's 87%. Because this is 0.87 of the one part. So that's 87%. So if you remember only your Henderson-Hasselbalch equation, which it will come up in your future life at some point, depending where you go. So if you remember that equation, then and you remember that when we have a buffer, we have both the conjugate base and the acid in the solution. Together, they're one part. So here it is. It's exactly what I have here, but with less numbers. Take a picture if you wish, or of the board. Okay. All right. So in titratable acidity, so it's measuring total acidity by titration. So we always titrate to get to the equivalence point or the end point. So we can determine this equivalence point by using an indicator or by measuring the pH. So the nth pH is 8.2, not 7. Why? Around 8.2, not 7. You'd think when you neutralize, you have a pH of 7. But the pH is slightly higher at neutralization. Why do you think? The conjugate base in your sample brings up the pH a little bit. So your end point or equivalence point is at pH 8.2. And this happens to be the pH at which your phenolphthalein indicator turns pink. So when you're titrating and you have phenolphthalein indicator, when the pH 8.2 is reached, you get a pink color. You know that this is the end of your titration. But we have a problem with the presence of phosphoric acid and carbonic acid. The inorganic acid, they buffer at pH 8.2. So if you have them in the system, it will be hard to get to the end point to see the color. You will practice in lab this titration with water, with the sample that you did not remove CO2 from it. You didn't bubble out CO2. With a sample that you have the CO2 in it, you will have carbonic acid, and you're trying to titrate. And then the carbonic acid, every time you have a pink color, it lasts few seconds and disappears, and you keep titrating. So you overshoot. So the solution for this kind of solution or beverages is you just measure the pH until you get 8.2. You disregard the color because your carbonic acid is going to, or phosphoric acid, they're going to continue to buffer. So you just measure when the pH reaches 8.2, that's your equivalence point. Might not be the end point because of the buffering capacity. So instead of overshooting your titration, you use pH meter and stop the titration when you get to 8.2. Also use the pH meter when you're titrating beverages or like tomato juice. Is really deep in color. You're not going to see that change in color, so we use a pH meter. So in the lab, in order to get the titratable acidity accurately, you need to standardize your NaOH solution. Because when you prepare a solution of NaOH, over time, it's going to pick up CO2 from the environment and it's going to produce sodium carbonate, which will reduce the actual concentration of your NaOH, and then you're going to over titrate because now you have a diluted solution. So what we do is what you're going to use in the lab is a water that has been boiled and the CO2 was removed from it by boiling. And then it's going to be in a big flask with an attachment to a trap. We call it ascaride trap. What is this trap? It has silica. The silica is coated with NaOH. So any CO2 that is on the surface above that water will be absorbed by the NaOH in that ascaride trap, and the water will be free of CO2. So you're going to practice using this water, and then also you're going to see the impact of having CO2 in your sample and how you're going to over titrate. So we standardize it. You're going to standardize it against a standard acid called potassium acid phthalate. So there is a process that you follow in the lab to standardize your NaOH with potassium acid phthalate. Okay. Now, calculating total acidity, the one thing that is different from all the other equations that we have done when at equilibrium of reaction is this. Instead of molecular weight, it's equivalent weight. Why? Because we're dealing with acids that might have more than one hydrogen in the equation. So the equivalent weight is the molecular weight divided by the number of equivalents. How many hydrogens? If I have acetic acid, molecular weight equal equivalent weight. So you have one carboxyl group. If I have citric acid, I take the molecular weight and divide it by 3. So I have 3 hydrogens. If I have malic acid, I take the molecular weight and divide it by 2. So that is important. That's the only difference in this equation from all the equations that you have used is instead of molecular weight, it's equivalent weight because we might have multiple hydrogens in the equation. So with that in mind, please solve this. And I think this is the last calculations we have. You got it, Taylor? Tyler. Why do I have a Taylor in my mouth? You both. Okay, Tyler, did you get it?
No,
No?
I lost.
You got lost a little bit? Okay, so you just look at the equation for titratable acidity, the same equation. Let me. So percent titratable acidity. In this case, we have citric acid, right? So we have 3 carboxyl groups. So 3 hydrogens are reacting. So percent titratable acidity, like always, you have the normality times the volume. To convert it to liter, from milliliter to liter, we divide by 1,000, sorry. And then you have here, because it's in percent volume, you can have the volume or you can have the weight of the sample, but this is going to be in volume of your sample. I believe, yeah. 15 milliliter of sample. So volume of the sample. And then you have the equivalent weight. And then you multiply by 100. So this is always the equivalence. At the equilibration of the reaction, you have the normality times volume, molecular weight or equivalent weight, divided by the weight of the sample or volume. In this case, it's going to be volume by volume or weight by volume and times 100. This is going to be weight by volume. All right. So what's the equivalent weight of your acid here? What do? You have the molecular weight is 192. Is the equivalent weight 192? What is it? 3 times less. So the equivalent weight, equivalent to one hydrogen transferring. So the equivalent weight equal molecular weight divided by number of equivalents. How many, what's the number of equivalents in this case? 3, because we have 3 carboxyl groups, 3 hydrogens. So the molecular weight is 190 grams per mole. 92?
Yeah.
192 then, okay. Divided by 3. So that is 64? No. Yeah, 64 grams per mole. All right, so you just apply the equation and put here 64 grams per mole. So you have the normality of the base, you have the volume of titration, you have the volume of the sample. What is your percent weight by volume? What did you get? 0.6, yes. Yes, thank you. So all you need to remember is your equivalent weight when you have an acid with more than 1 carboxyl groups, you have more than 1 hydrogen, you want to account for that. If you have acetic acid, it's divided by 1. No. When you have malic acid, you have 2. When you have citric acid, you have 3. But I will tell you in the exam, I will tell you, okay, citric acid has 3 pKa's. If I tell you that you know that we have 3 hydrogens. If I say 2 pKa's, you know that we have 2. Okay, so I will give you that in the exam. All right, so 0.6. The last thing I have is just to put things in perspective. Percent titratable acidity is really low. You know, maximum one is close to 5 in lime, 5 to 8 in lemons and limes. But in general, percent titratable acidity is low. Look, this is kind of, when you calculate it in an exam, if it is low, then you'll know that your calculation is potentially correct. So titratable acidity, we always take the predominant acid. Sometimes you have multiple acids in your fruit juice, for example. So we always calculate based on the predominant acid. And then there is the Brix to acid ratio that you probably hear of. And this is a predictor of acid flavor and maturity of your fruit juice. And the last bit here is volatile acidity. This is a quality indicator for wine. So if wine has vinegar, it's not a good wine. So what you would do is you take your wine, you measure titratable acidity, then boil it off, your acidic acid will evaporate, and measure titratable acidity again. The difference will be acetic acid. And the higher acidic acid you have, the lower is the quality of your wine. This is what you're going to be doing next week. So determine acidity, you're going to plot malic acid titration curve, and that's it. So next week, so I won't be here Monday and Wednesday, but you don't get off. We have a wonderful guest lecturer who's going to give you a lecture on vitamins and a lecture on minerals. Can you guess who that person is? No. I mean, Gary is wonderful, but he's not the vitamin and mineral guy. He's the vitamin and mineral guy. No. Danielle. Oh, yeah. So if you don't know him, please come and know him. He's super engaging, super fun. He'll make it relevant from a nutrition perspective as well as food science. So that will be Monday and Wednesday, and I will see you on Friday of next week. Have a wonderful break. Enjoy the food. And that's it.